Hi guys. So in this video we're going to talk about a few more rules for how to find derivatives, and those are the product rule and the quotient rule. Okay, so the next rule that we are going to look at is the product rule. And to introduce it, I'm going to show you a proof of it. You do not need to write this proof down. We will get to the TTK at the end. I will let you know when we're at the TTK part. For now, just watch, observe. Okay, so we're going to go back to that definition of the derivative. And let's say that we have some function h of x, which is the product of two other functions. These could be polynomial functions, they could be trig functions, there could be any kind of two functions that are being multiplied together. Okay, we'll call them f of x and g of x. So if we want to evaluate the derivative h prime of x, we know that using the definition of the derivative, it's going to be the limit as h approaches 0 of h of x plus h minus h of x all over h. Okay, so we can split that up now because we know that this capital H function of x plus h is going to be f of x plus h times g of x plus h. And then we know that this minus h of x is going to be minus that product, f times g. Okay, so carrying that forward, here, let me just show you what's happening here. We are just adding in something that we're going to use later. We are both adding it and subtracting it, which is okay algebraically. It's like if you add 2 and you subtract 2 and they cancel out. That's all we're doing here because these two pieces here are something that's going to come in handy in a moment. Don't worry about where they came from. Just know that algebraically it's okay to put them in there. We're doing a proof. Like I said, you don't need to be writing any of this down, and you're not going to be expected to do something like this on a quiz or on a test or on the AP exam. I'm just showing you where this property that I'm about to reveal comes from. Okay, so don't freak out. Okay, so with that sum and difference, that is just the same term being added and subtracted, if we move that around a little bit, okay, to go with kind of these two different pieces. So from that original piece, that product with the x plus h's is still here in the front. The difference, or sorry, the difference of the other product, which is f times g, has moved back here to the back. So this next step, we've just rearranged some stuff, okay? With that, the reason that we have done that is because now we have like terms. So in that front piece, there are now like terms that there's a GCF you can factor out, rather, of an f of x plus h. So we have just factored that out to make a new fraction. In that back piece, it also has a like term of g of x, which we factor out at the front of that piece. Because this whole big thing is a sum, it is okay to split it into two fractions with the same denominator. So again, we have not broken any rules of algebra, and we're not going to. Okay, with that, we can then use our limit properties and separate this into the limit of each of these products. So the limit on the left as h approaches 0, the limit on the right as h approaches 0 for both of these, okay? Then we can further split up this limit so that you've got the limit of f of x plus h times limit of that difference with the g's plus limit of g times limit of the f difference quotient. Okay, so from all of that, then we keep going. Okay, this is where we were just at a moment ago. Nothing has changed, just moving it up the page. Okay, so the limit as h approaches 0 of f of x plus h, remember you can just substitute that 0 in for h and you just get f of x. Again, we don't know what f of x is, we're just speaking in very general terms here. Same thing happens with the limit as h approaches 0 of g of x, because this piece there is nowhere to plug in that 0, so that means that piece just is g of x. So notice what this has given us. We have f of x times the limit of the difference quotient of g plus g of x times limit of the difference quotient of f. And you know that that limit for the g's is the same thing as g prime of x, and the limit for the f x is the same as f prime of x. And that right there is the product rule. Okay, so I said I would warn you when we got to the TTK. Here's the TTK. Now that's kind of an ugly way of writing it. Sometimes the Leibniz notation is better, sometimes it's not so great. Here are the two ways at the bottom that I would recommend writing this TTK. Pick your favorite. But the idea is that you've got the original first function f of x times the derivative of the second function plus, and then flip-flop. So f of x times g prime of x plus g of x times f prime of x. And you can write this in either order. It does not matter. Because it's a sum in the middle, it doesn't matter. Each original function from the original product is getting multiplied times the derivative of the other. So now we'll look at an example of how to apply this. Okay, so this example says find f prime of 1 if f of x equals 3x squared minus 5x plus 4 times x squared minus 5. So the product rule allows us to kind of skip the whole distributing business here, because it would be perfectly valid if you wanted to distribute the 3x squared and then distribute the minus 5x and then distribute the 4. You could do that. Or you could use the product rule. So what I'm going to do first of all is I'm going to kind of just label each of these functions within it. I'm going to give them names. F is already taken, so I'm going to call them g of x and h of x. So what the product rule tells us then is that the derivative f prime of x is going to equal g of x times the derivative of h of x plus h of x times the derivative of g of x. So we can find those derivatives now using the power rule like we talked about yesterday. So let's do that. So first of all, this first piece here we have is just the original function g of x. So I'm just going to write that whole thing here, 3x squared minus 5x plus 4. And then that's times h prime of x. So we go to h of x, and the derivative of x squared minus 5 is going to be just 2x, because that minus 5 goes to 0. So it's just 2x. Okay, so that's g of x times h prime of x plus, now we're going to have h of x, so copy and paste, x squared minus 5 times, now we need g prime of x, so g of x, 3x squared becomes 6x, minus 5x becomes minus 5, plus 4 goes to 0. Okay, now, as I've said before, if this were an AP free response, once you're done with the calculus portion, you could stop right there. You could say, this is the answer, ha 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 ha, and just stop. But just for the sake of being thorough, let's go ahead and simplify this a little bit. So we're going to have to distribute that 2x in the first piece. So that's going to give us 6x to the third minus 10x squared plus 8x. And then in the back, if we multiply that out, distribute or FOIL or however you were taught, let's see, that'll give us 6x to the third minus 5x squared minus 30x plus 25. Then we can go through and combine our like terms. We've got 6x to the third plus 6x to the third, so that's 12x cubed. Then we've got minus 10x squared minus 5x squared, so that's minus 15x squared. Plus 8x minus 30x, so minus 22x. And then plus 25. So, of course, if you're doing a multiple choice question on the AP exam, it's going to look like this latter answer here. But if you're doing a free response and you can stop as soon as you're done with the calculus, then you can just stop right there basically as soon as you're finished with the product rule. Okay, so that's it. That's the product rule. Now right now you might be thinking, well, why not just multiply it out and then take the derivative? And that's fine for a polynomial. But later on, excuse me, we're going to look at functions where you can't do that. Like if you have x times the sine of x, there is no foiling that out. Okay? If you've got, let's say, a log function times a trig function, you can't just multiply that out. There's nothing to do. Just right now, because we've only talked about taking derivatives of polynomials, that's what I'm using to show you this. But later on, you will have to use the product rule in different situations. Okay, so it makes sense that if we're going to talk about how to take the derivative of a product of two functions when you're multiplying, then we're also going to talk about what to do when you're dividing two functions. And for this, we have one more TTK, which is the quotient rule. Now, I've written it here with Leibniz notation, but you also could think of it as being like this. If you're taking the derivative of a function f over some other function g, so in other words, you've got a rational function, some function on top, some function on bottom, it's g of x times f prime of x minus f of x times g prime of x. All of this is over g of x squared. Now, this one, the order on top is very particular because it's subtraction. The product rule is flexible because you're adding the two things that you get from the product rule, but here we're subtracting. So the order is very specific on this one. It has to be the denominator function times the derivative of the numerator minus the numerator times, etc. Okay. So, first of all, I'm not going to show you the proof of this one because it's arduous. It's way worse than that product rule proof that we just looked at. So don't worry about it. No, there is a proof. You can look it up if you're really interested. We're not going to worry about it though. So just trust me on this one. Okay? So here is a way to remember the quotient rule. And it's going to sound a little silly at first. If you think of the numerator as high and as low, it's going to sound like yodeling. Low d high minus high d low over low low. So low being like your g of x down there as the denominator, it's low d high. So g of x times derivative of the numerator, that's your f prime of x, minus f prime of x high times the derivative of the numerator, d low, all over the denominator squared. That's your g of x squared, or low low, because it's g of x times g of x. It sounds silly, but trust me, this is the best way to remember the quotient rule. Also, something to keep in mind with this, if you get confused as to which one's which on top, remember that the endings rhyme. So they both should end in something with g of x. Low d high minus high d low over low low. They rhyme. Think of it that way. Okay, so here's an example of how we can use the quotient rule. So find the equation of the tangent line at x equals -2 to the curve y equals blah, blah, blah. Okay, so first let's find our function for y prime, the derivative. Okay, so it starts off low d high. So that means we take the denominator function, 2x plus 5, multiply that times the derivative of the numerator, d high. So the derivative of 3x minus 1 is 3. Then it's minus high, so 3x minus 1, d low, derivative of 2x plus 5 is just 2 because it's linear. All this is over low low, which means you can just take that denominator and write quantity squared. So we can simplify this a bit to get our y prime function, and then we can take that -2 and plug it in and then find our slope at that point. So if we keep going, we distribute that 3 on top, so you'll get 6x plus 15 minus, I'm going to put all of this second piece into parentheses, I'm going to distribute that 2, so we'll get 6x minus 2 over, and then I'm not going to even bother foiling out that bottom piece because we're about to plug in something for x in a second. So it's not even worth the effort. Okay, on top, notice what's about to happen. That 6x and 6x cancel out. So we have 15 minus negative 2, it just becomes 17 on top over 2x plus 5 squared. Okay, that's our derivative function. Now we've been told to find the equation of the tangent line at x equals negative 2 to the curve. All right, so we're going to plug in that negative 2. So we're going to take that negative 2 and just plug that in for x. So we'll get that y prime at this point. 17 over, so negative 2 times 2 gives you that negative 4 plus 5 quantity squared. Okay, well on the bottom it actually cleans up quite nicely because you just get 1 squared, which is 1. So that whole piece just becomes 17. So that is the slope of the tangent line at that point. We have been asked to find the equation of the tangent line. So remember that this is where your point slope form is going to come in handy. And this y prime here, that's m, right? Because that's the slope of this tangent line. We have x1, that is this negative 2. We need y1, so we just go back to the original function and we plug in that x value. So let's see, that'll be negative 6 minus 1 over negative 4 plus 5. So we get negative 4 plus 5. So you get negative 7 over negative 4 plus 5 is 1. So we get that y1, when we plug in x1, just gives us negative 7. So now we can write the equation of the tangent line. It's just going to be y minus, it's negative 7, so we'll just turn that into a plus 7. Y minus y1 equals m, we said was 17, parentheses, x minus x1 is negative 2, so we'll just make it a plus. So the equation of the tangent line to that curve is just going to be y plus 7 equals 17 times x plus 2. And again, this is the equation. You don't have to have mx plus b every single time. This saves you so much work. So do it this way. So just because we have the quotient rule does not mean that every time you have to use it. If you have something over a monomial, you don't necessarily have to use the quotient rule. So here's what I mean. If we just have 1 over 3x, then we can use a little bit of algebra here to rewrite this differently. So what I mean by that is if you think of this as being 1/3 times 1 over x, because that x is in the denominator, so it would have to be 1 over x like this. Well, 1 over x is the same thing as x to the negative first power. Well, then you can take the derivative of that just using the power rule now. You can say y prime equals, multiply that negative 1 times the 1/3, you get negative 1/3. Decrease the power by 1, so negative 1 minus 1 is negative 2. And there's your derivative. You could do this with the quotient rule. Just to show you, you can do the same thing. I'm going to do that here in a different color. You don't have to do this though, just watch. Okay, if we have that same function, 1 over 3x, and we apply the quotient rule, you'll get low 3x, d high, derivative of 1, the constant, so that's 0, minus high d low over low. Make sure you put that in parentheses because it's not just the x that's getting squared, it's also the 9. So then if we simplify, on top you get 0 minus 3, so that's just negative 3. Over, on the bottom we get 9x squared. Okay, well negative 3 over 9 simplifies to give you 1/3. And guess what? If you have that x squared in the denominator, that's the same thing as x to the negative second. So those are both the same. So either method works. You'll get the same answer, but gosh, it's a lot easier if you don't have to use the quotient rule. So just be mindful of that. If you've got something like a monomial down here, you can avoid the quotient rule. And we'll look at a few more examples of these. Okay, so here's another example. Y equals pi over 2x to the negative third. Okay, again, first of all, let's take that constant out in front. We'll say it's pi over 2 times 1 over x to the third. So we're just dealing with the x separately, negative third, from everything else. Okay, well now that we've done that, notice we've got a negative exponent in the denominator, which means that you can rewrite this function, pi over 2 is just chilling, but then 1 over x to the negative third, if you bring it out of the denominator, it loses that negative exponent, and it just becomes pi over 2 times x cubed. Then, to take the derivative of that, there's no quotient rule at all, because pi over 2 is a scalar, so it just becomes 3 times pi over 2, so 3 pi over 2 times x squared. And that's it. You just multiply to 3 times what's out in front. You're just applying the normal power rule here, decrease the power by 1. Pi is a scalar. It's a coefficient. It's 3.14, etc., etc., etc. Okay? So it's not a variable. We don't treat it like a variable when we derive just because you write it with something that doesn't look like a number. It is a number. So that's it. Okay, one last example of how we can use algebra to avoid the quotient rule. Recall some properties of exponents. Well, what I'm going to use here is a rational exponent. We're going to use this a lot in calculus because we want to avoid things like rational functions like this if we can. If we can get it back down to just a single polynomial, then we can just apply the power rule. It becomes much easier. So recall from your algebra days that if we just have the square root of x, that is the same thing as x to the 1/2 power. So we can say this is x to the 1/2 over x to the third. Then remember that if you have a quotient of 2 different powers of x, that you can rewrite this expression as the difference of the powers. You can say this whole thing is just x to the 1/2 minus 3 power. Okay, well 1/2 minus 3, it's negative 2.5, or it's x to the negative 5 over 2. And that's just y. I haven't done any calculus yet. Okay, so if you're not comfortable with exponents, that might be something you need to go Google and review, or go spend some time with your old friend Con on his academy, etc. So now we can take the derivative of that. Again, we don't have to use the quotient rule. We got rid of the quotient. If you didn't do that, it would still work, but it's just going to be easier not to. So we've got y prime equals, we're going to multiply that negative 5 over 2 to the front, decrease the power by 1. So if you've got negative 5 over 2, and you're subtracting 1 from that, you need the common denominator of 2. It's like we're subtracting 2 over 2, so this becomes to the negative 7 over 2 power. And again, for the purpose of free responses, it's calculus. You can stop right there. Okay, so that's the quotient rule and the product rule.